Okay, for the question 1A, this is the written code. This is the output of the code that has been run. Okay, next for the question 1B, this is the code and the length is 61. Okay, for the question 1C, here is the code that has been written. This is the output and X1N is periodic. Okay, for the question 1D, this is the modified code with the following properties. Okay, this is the output for the question 1D. Okay, for the question 1E, this is the mathematical approach for the X2N. Okay, for the question 1F, this is the difference between X1N and X2N.
So here we are going to question number 2, which is we need to modify the coding given with the new equation. So from here we know that the alpha is 0.3, omega is 6, and the range is from 0 to 6. After we running the new modified coding, so here is the result of the real and imaginary part graph and magnitude and phase graph. Question 3a, which is we need to generate coding to plot H1n, H2n, Xn using subplot, and the right side figure is showing the result. Question 3b, which is using convolution to compute the value of Vn and Yn. So the result for both Vn and Yn was plotted using subplot like the left side figure. Question 3c, which is we need to reverse the order system. Then the new Vn and Yn generated using subplot as you can see at the right side figure. Question 3d, the difference in value of Vn in part B and part C is because in part B we use the equation Xn multiplied by H1n, and then in part C we use Xn multiplied by H2n. And then the reason of Yn is equal in part B and part C, it is because the equation at both sides will be the same at the end. So we can conclude that Yn in part B is equal to Yn in part C.
Okay, this is the code that has been written for question 4A. This is the output for the question 4A. Okay, for the question 4B, this is all the integration steps. Okay, this is the answer for the question 4C.
In question A, we calculate the impulse response HT, which turned out to be a shape size function centered at 3 t equal to 3. This carry show the delay effect from the phase terms e power of negative j 3 omega. In question B, we using size 40 as our input. The signal contains high frequency components above the filter cutoff. After filtering, the output become lower in amplitude, showing that the filter removed the high frequency, leaving only the lower frequency constant. In question C, we improve a quadratic square wave using Fourier series. Square waves have many high-frequency harmony. After filtering, harmony are removed, and the output look like a smoothie size wave, mainly representing the fundamental frequency.
Question 6a give out the transfer function above HS and the coding which to need to run, and the coding is to illustrate the Matlab function tf zbk0 pole tf data is stable f print tf residue and pc maps, and the output of the coding are the pole 0 maps included in the slide. Question 6b is the continuation of question 6a. Instead, we need to find the impulse response using the residue functions. As you can see, the impulse response ht is plotted beside, and the code from the function of in question 6a using the residue functions. So question 6c give the differential equation as shown in the slide, and we need to derive it manually using Laplace to find the transfer function before we can actually start coding. When we run code for question 6c, the comment window will tell us about is the system is stable, which is true, and it will tell us the residue, which is 1, -1, 1, and the poles, which is -3, -2, -2. From the residue and poles from the codes, we can actually inverse Laplace it to find the final impulse response as shown in the slide, and this show the system is casual and the ROC is at the right half plane to the right of the rightmost pole.